Guys, this is the Doppler Effect lab that we did where we went out and blew the car horn. And notice at the very, very top it says the period of the horn source while stationary. And then the second one down here says the period of the horn source while moving. Okay. And there's five questions down here, actually 6 questions down here that I want you to answer first. But let's do it number 5, first of all, because I made a boo-boo on there. I want you to change that 88 degrees, because it wasn't near that hot out there when we went out. That should be a 73. Well, actually, it's 23 degrees Celsius, so however you want to do that, but it's 23 degrees Celsius, I think is a better way to do it. So if you use that formula that we used the other day, to figure out the speed of sound, it's 331 times the square root of the temperature in Kelvin, so it's 273 plus 23 degrees all over 273. And when you get that, you should be somewhere in the general vicinity of 345 meters per second being the speed of sound the other day. Okay, so I just want to make sure that you knew how to do that, especially since I screwed it up. So let's now look at the period of the stationary horn at the very, very top graph. Well, the way you get the period is by figuring out how much time per wave. Well, if you look at the very, very bottom here, it says, I'm sorry that this is so scrunched up. Let's see this. It's better here. The time on the bottom is 0.02. That's a little bit bigger for you. I'm sorry, it's 0.03. If I can read it myself. Yeah, 0.03 seconds. And so we have to figure out how much time, 0.03 seconds, is per wave. Well, if you count these waves, I'm going to start right here. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. I got 9 loops going across if you start with 0. But it doesn't start at the top of the loop, it starts down here. And this also ends as the wave's going back up. So you basically have 10 waves going across this particular screen, and 0.02 seconds for that 10 waves to go across. So in number 1, I want you to figure out what is the time per wave. Now that you have that, feel free to stop this at any time. I want to skip down to number 3. Now number 3 down here says, what is the frequency of the stationary horn? Well, you got to remember that frequency is the same thing as 1 over the period. So instead of having the amount of time per waves, frequency is the number of waves per second. So do that same thing that you just did, counting the waves and counting the time, but this time figure out how many hertz you have, or how many waves per second you have, and get that for number 3. Once again, feel free to stop this at any time. I'm going to go to number 2 now. Number 2, it's really, really tricky. With number 2, the car was moving, so I have engine noise coming into the microphone. I also have the noise of the air. When it hits the horn, it actually causes another frequency. So if you look really, really close at this, you can see that the waves are actually in groups of 3. So there's a group of 3. Here's a smaller group of 3 with destructive interference. Here's one that's it's a combination of destructive and constructive. So that's a group of 3 right there. Here's another group of 3. So if I count the groups of 3s, it's almost 7 if you sort of eyeball it. Now, I know I'm fudging this here. So if I look at that each group of 3 as being 1 wave, I have basically 7 waves going across there. Now be careful, because down here on the bottom, instead of 0.03, I now have 0.02 down here on the bottom now. Okay, that's a 2. Make that a little bit bigger so you can see it. So I need you to do the same thing that you did in number 1, but now you're going to use that second graph. So you got 7 waves divided by the time. I'm sorry, the time of 0.02 seconds divided by the 7 waves. And we're going to do the same thing for number 4 that we did in number 3, but you're going to find the frequency of that. Now comes the tricky part, because this becomes algebraically a little tough. Let's figure out what the speed of the car was based on these particular data matches. So, on number one, hi Taryn, that's Taryn everybody. On number one, you have the frequency of the horn when it was stationary, so I'm going to call that F sub S. On number two, you have the moving car, so that's going to be the frequency that you actually observed. This next one down, I'm putting frequencies up here, I'm at periods, my fault. So this is going to be the time of the stationary object. This is going to be the period of the observed object. On three, it's going to be the frequency of the stationary object or the source. My pen's running out of ink when you know it. So I have the frequency of the stationary object here. It's still not taping very well here. And on number four, that's going to be the frequency that you actually observe. I'm sorry, this is not working. I'm going to go back up here. All right, I'm sorry, everybody's coming into class here. So this is going to be the frequency of the stationary source. This is going to be four is going to be the frequency of the observer. You have to figure out what is the velocity of the source coming at you. Now, we were standing still, so the velocity of the observer is 0 on this case. Okay, so you're looking to find the velocity of the stationary source. Don't forget the formula that you're going to use is the frequency of the observer equals the frequency of the source times the speed of sound. The top one is plus the velocity of the observer, and this one is minus the velocity of the source. And remember, they're coming towards you on this, so that's the formula that you're going to use on this. So make sure you get that done by Tuesday as well. Thank you. Good.